Yusuf Khan with you. So basically, when I was making this basics of microwave propagation, so I just thought that I have missed this main equation. It's called the Friis equation. It is used a lot in microwave when you are planning your link budget. So mainly your link budget depends a lot on the Friis equation, and we will try to go in a bit of detail, and I will show you that how this Friis equation is used and how it is built. Here I will not go in a lot of detail because I also know that a lot of detail is a bit more. But if any one of you is in, for example, someone in education field, he's studying these things and he has a question or someone really wants to go inside, you can always contact me. But let's start. So basically, in the last lecture 6A, we finished on this point, the free space loss point, and now we will build over it. But before moving ahead, I would like to show you one thing, because in my last lecture I also tried to convey this, that I will try to show you these things in path loss as much as possible. I mean, so I will try to show you that what is this exactly and how and where you can see this in path loss in actual, I mean. So as I was mentioning, but because this is log of 10 of distance and log of 10 of the frequency. So if we put distance and frequency as, I mean, like distance, if we put as 10 kilometer and frequency we put as 10 gigahertz. So log of 10 with the base, I mean, base 10 log of 10 is 1. I mean, when you take a log of 10 and the base of the log is also 10, then the resultant is 1. I mean, if we keep 10 in place of distance and we keep 10 in place of frequency, then this log of 10 value will become 1. So this part will become 20 and this part will also become 20, and this will remain, this is a constant value. So this will be 40 and the total value will become 132.45. So let me show you. Here in path loss, I just try to make a 10 kilometer link with nothing. I mean, it's just to show you. The link is also not exactly 10. I try to make it 10, but it is a bit larger than 10, not too much. I mean, I will show you. Like in terrain data, if you see, this is a bit more than 10. So the result value will not be 132.45. It should be a very small, more than 132.45. So what is the value? Let us see. And if you see here, this is the free space loss. This is the value, this thing, free space loss. And we said that for a 10 kilometer length and 10 gigahertz frequency, it will be 132.45. And as I told you that my total length is a bit more, not exactly, I mean, this is 10.1. So it is 132.51. I mean, a bit more. 132.45 should be with the exact 10, because it is not exact 10, so it is 132.51. So it was just to show you that these equations are actual equations. I mean, they are actually put in path loss. Path loss does not do anything from its own. It takes all the math. It does the math for you. So we will see in the same way, we will see all other things as well, whatever I will be able to tell you. So we check that this free space loss in path loss is calculated with the help of the same equation. So let's go further. So was only the free space loss part. So what Friis do? Friis went one step further, I mean, because now we have free space loss. So if we need to get the received power value as well, then what Friis did is that he did a small experiment and he used this empirical formula to calculate these values. Like he used one isotropic antenna which was provided with some wave, some oscillating signal, and it was received at some distance. And he came to know that the power receive object power transmit depends on the aperture of receive and transmit divided by distance and lambda. And as we know, let me show you also, like here if you see, the aperture is basically lambda square by 4 pi. So if we put both the aperture values, so this will be lambda square by 4 pi, this will also be lambda square by 4 pi. So 1 lambda square will be gone, I mean, because of this. So we will have only 1 lambda square here and 2 times 4 pi also. So this will, this was the traditional Friis equation, but in contemporary formula, what we did is that we removed this aperture and we use the antenna gains, because aperture is a bit, you can say, a bit confusing value, and because antenna gain basically depends on a bit more values, and it's not only the aperture. Aperture may be same for two antennas, but one antenna may have a higher gain because of how it is made and what kind of material is used. So gain is a more better value with respect to aperture. So the contemporary formula for the received power uses antenna gains, and it is almost calculated from here that you add power transmit plus gain of transmit and gain of receive, and then this is a value of the free space loss. And I will not go in detail, but total value is basically minus from this. I mean, like if you remember here, the free space loss is a positive number. But this value is basically, it's the inverse of free space loss. It is not actually the free space loss. So this value will become negative, and whatever is free space loss will be deducted from these three things, like from power transmit plus one gain plus second gain minus free space loss. It will give you the power receive. I will not go in a lot of detail, as I told you that if anyone needs to know further, then he may contact me or he may give a comment. So I will not go very much further, but this is how the receive power is calculated. I will try to show you this in path loss as well in some of my next videos. But one thing that I just thought that I will add here, when I was in a company where I used to do a lot of interviews as well to hire new people, I used to ask this one question from them, that like here it is an antenna, that basically antenna is a passive device. You are not giving any power to the antenna. Antenna don't take any power. If someone thinks that antenna has been giving, I mean, you are giving some power to the antenna, then let me correct you. I mean, before you make that claim. Basically, from the IDU, we send some kind of power to the ODU, because ODU is an active equipment. ODU has some active things. I mean, ODU is doing. Audio also has a gain. I mean, whenever it is receiving a frequency, it's kind of pre-amplifying it, and because it's doing some frequency conversions as well, and it is doing three, four things. So that's why it needs some power, but that power is not fed to the antenna. Antenna don't use any power. Antenna is a fully passive device. So I used to ask this from the people that, I mean, if antenna is really a passive device, then how it has a gain? Because a passive device should not have any gain generally, but antenna has a gain. So why it is that? So I will not keep you waiting for this question. I will answer it right now. And you can see it from the dB values as well. You can see that power receive is in dB, power transmit is in dB, but the gain of transmit and gain of receive antenna is in dBi. So why it is in dBi is because basically when we were in our previous lecture also, when we were studying this, we say that there are isotropic antennas on both sides. But in actual, we have a dish here. We have a dish here. If you put a dish here and you put a dish here, so what happens is that the transmitter become directive. I mean, you give directivity to the transmitter. This isotropic antenna right now, its waves are spreading in all directions. But if you assume that there is a dish here which has a curve, so that dish will converge all the power and send it in only one direction. That's why, if you remember, we have an antenna lobe. There's a main lobe and there are secondary, I mean side lobes. So most of the power goes through the main lobe. More than 60% or 70% power goes through the main lobe. So there's a difference. I mean, when you have an isotropic antenna, a very little power is going in the front direction because power is spreading in all directions. But when you put a dish, on the back of antenna, and antenna is for here, and it is transmitting in all these directions, but that whatever is transmitted is being directed to the front of the antenna. So you typically have a gain. I mean, now the power which is going in the front direction is much more than it was going when it was a simple isotropic antenna without any directivity given to it. And same goes for the receiver, because the receiver has some effective area, some aperture of it. If it was a very small isotropic antenna, then it should be receiving a very little part of the power which is being sent. But now, as it is a dish, so it is converging all the power that it receives, it converges to one point. So basically we have a kind of gain, but that gain is not an actual gain, but it's a gain with respect to isotropic antenna. If you have an isotropic antenna and if you have a directional antenna, then what is the ratio between the power which is received? This becomes the gain of antenna. So I hope that I'm not making it more difficult for you. It's a bit simple also, so you will have some idea that why we have antenna gain, why we call it antenna gain, because it's a gain with respect to the isotropic antenna. So this is how we use the Friis equation. I will show you in my next lecture. I'll show you it in path loss as well, just like I show you this free space loss in path loss, how it is calculated, how it is shown. Same way we will see this as well. I will have to design a full link, and then I will show you that what are the antenna gains and what value should come, and exactly we will see the same value. I will make a very small video on that as well as my next video. But up till now, I hope that you should be following along with me. So we are coming, like we come one step ahead. I mean, after free space loss, now we are able to calculate the actual receive power as well. So I hope you will like this video, and you will, if you have any question, if there is some place where you feel that you need some more thought on that, so you can comment on my video, you can ask the questions from me, and I will hopefully reply you. See you in my next video. Goodbye.